Picture standing on a beach near the equator today, palm trees, blazing sun, warm water lapping at your feet. Now picture, in the rock beneath that same beach, unmistakable scars left by glaciers, scratched boulders, ice-drop debris, the signature of a frozen sea. That's not hypothetical. It's exactly what geologists found. And it took a century to explain. These rocks are called tillites, cemented, jumbled debris. Only glaciers leave behind. Scratched pebbles, boulders dropped far from where they formed, sediment scraped and smeared by moving ice. Geologists have found tillites like these on nearly every continent, dated to a stretch of deep time called the Neoproterozoic, roughly 717 to 635 million years ago. Tillitites by themselves aren't strange. Ice ages come and go throughout Earth's history. The trouble started when geologists worked out exactly where on the globe these particular tillitites had formed, because the answer, again and again, made no sense at all. To find out where a rock formed, geologists use paleomagnetism. Certain minerals, as they cool and crystallize, act like tiny frozen compasses. They lock in the direction and angle of Earth's magnetic field at that exact place and moment, and keep that memory for hundreds of millions of years. Here's the trick that makes it useful. That magnetic needle doesn't just point north-south, it also dips steeply near the poles, almost flat near the equator. Measure the dip angle preserved in a rock, and you can calculate the latitude where it formed, even if the continent has since drifted far away. In 1964, a British geologist named Brian Harland measured exactly this in glacial tillitites from Svalbard and East Greenland. And the dip angles he found were shockingly shallow, the kind you'd expect not near a pole, but close to the tropics. Harland had, in effect, found glaciers on a beach. His paleomagnetic readings said these ice-scarred rocks had formed at low latitude, not on some tall mountain, but near sea level in the tropics. He flagged it as a genuine puzzle in the 1960s. Almost nobody knew what to make of it. Stop and feel how strange that is. Glaciers form because a place is cold. The tropics are the hottest band on the planet, drenched in the most direct sunlight Earth receives. Finding sea level glacial debris there is like finding a snowman that built itself in the middle of a desert at noon. And this wasn't some minor mountain glacier creeping down from a peak. The evidence, boulders dropped by floating ice directly into marine sediment, showed ice reaching all the way to sea level over open ocean at the equator. If this was right, even the warmest, lowest parts of the entire planet had frozen. Naturally, many scientists were skeptical. Maybe the paleomagnetic readings were somehow corrupted. Maybe the ancient magnetic poles had wandered somewhere strange. For years, this stayed a fringe curiosity filed away as probably an error, because the alternative, an equator-to-equator ice age, seemed almost physically impossible. But through the 1970s and 80s, more sites kept turning up telling the same story. Tillites in Namibia, in China, in Scotland, and one of the most convincing examples of all, a rugged formation in South Australia called the Elatina Formation. At Elatina, geologists ran a rigorous test, checking whether the rock's magnetism was locked in before or after it had been folded and slumped by later geologic disturbance. The magnetism turned out to be original, and it placed this glacial deposit within a few degrees of the equator. That fold test mattered enormously. It ruled out the easy excuse that the magnetism had simply been reset or scrambled later. The signal was original, it was clean, and it was tropical. The case for genuinely equatorial ice was getting very hard to wave away. By the late 1980s, the picture worldwide was consistent and strange. Not once, but at least twice in deep time, glacial debris had been dropped at or near the equator, at sea level, on multiple separate continents. This was not a fluke of one bad reading. It was a global signature. These two icy episodes now have names. The older, running from about 707 to 660 million years ago, is called the Sturtian glaciation. The younger, from roughly 600 and 635 million years ago, is the Marinoan. Together, they define a stretch of Earth's history nicknamed the Cryogenian, literally the Age of Ice. So here was a real, unresolved mystery sitting in the rock record. Something had frozen the ocean at the equator not once, but twice, for millions of years apiece. No ice age in the more recent past. Not even the depths of the last ice age comes close to that. What could possibly do this? It would take a very particular kind of scientist to actually propose an answer. Someone comfortable with wild ideas, deeply versed in both rock magnetism and planetary chemistry, and unbothered by how strange the implications sounded. At Caltech in the early 1990s, that person was a geobiologist named Joseph Kirschvink. Kirschvink didn't just accept that tropical glaciation had happened. He asked the harder question, what physical mechanism could actually freeze an entire planet's ocean all the way to the equator? And, just as importantly, how would such a frozen world ever manage to thaw back out again? His answer began with something deceptively simple, the color of ice itself. White reflects sunlight. And under exactly the right conditions, that single fact about reflectivity can spiral out of control, until it swallows an entire world. Every ice sheet on Earth does one simple thing extremely well: it reflects sunlight. Scientists call this property albedo, the fraction of light a surface bounces back rather than absorbs. Fresh snow and ice can reflect 80% or more of the sunlight that hits them. Dark ocean water absorbs the vast majority instead. Now add the feedback. More ice means more sunlight reflected, which means a cooler planet, which means even more ice forms. Cooler planet, more ice, more reflection, cooler still. It's a loop, feeding on itself, and like a lot of feedback loops, the real question is whether anything stops it. On the Earth we're used to, this loop is self-limiting. Ice caps grow in winter and retreat in summer. Polar ice stays roughly bounded near the poles, and the system settles into balance. For most of Earth's history, that has been the normal, comforting story. But climate physicists found something troubling buried in the equations. Once the edge of the ice sheet creeps down to roughly 30 degrees latitude, about a third of the way from pole to equator, the loop stops being self-limiting. Past that line, it becomes genuinely unstoppable. Why there, specifically? Because the tropics receive the most direct, most intense sunlight on the whole planet. Once that especially bright band starts turning reflective white instead of light-absorbing dark, the planet loses an enormous amount of incoming heat all at once, and the cooling accelerates faster than it can be answered. Kirschvink recognized this as bistability. Earth's climate has not one stable resting point, but two, something like today's mild world, and a fully frozen white one, with an unstable edge between them. Nudge the ice line past that edge, and there's no comfortable middle to settle into. The system runs all the way to the far end. In 1992, Kirschvink wrote up this idea, remarkably, in just 7 paragraphs, tucked into a 1,400-page academic volume about ancient life called The Proterozoic Biosphere. It wasn't peer-reviewed. It wasn't flashy. But it proposed for the first time a real physical mechanism for tropical glaciation. And in that short paper, Kirschvink gave the whole scenario an unforgettable name: Snowball Earth. A planet frozen edge to edge, pole to pole, and equator to equator, an entire world turned briefly into one enormous ball of ice and snow. Kirschvink backed the idea with a second clue: banded iron formations, striped rusty rocks that normally only form when oceans are cut off from oxygen and rich in dissolved iron. Largely absent for over 1 billion years, these formations mysteriously reappear right alongside the Neoproterozoic glacial deposits, as if the ocean had been sealed shut. His real masterstroke, though, was explaining the escape. With the entire ocean under ice, the normal process that pulls carbon dioxide out of the air, rainwater slowly dissolving exposed rock, called silicate weathering, would grind almost completely to a halt. No exposed, unfrozen rock means no weathering, means no natural break on carbon dioxide. But volcanoes don't care what the surface looks like. Deep underground, they keep erupting and outgassing carbon dioxide regardless of whether the world above is frozen solid. With nothing pulling that CO2 back out of the sky, it simply has nowhere left to go. So carbon dioxide just accumulates. Year after year, millennium after millennium, with the normal removal process switched off, it slowly piles up in the atmosphere, like a pressure cooker with the safety valve welded shut, building for millions of years without release. Eventually, carbon dioxide reaches a genuinely staggering level, something like 350 times today's atmospheric concentration. At that point, the greenhouse effect becomes so overwhelming, it can finally outmuscle the ice's blinding reflectivity, and the frozen world begins, at last, to melt. And once triggered, the thaw wouldn't creep. With that much greenhouse gas stacked up, deglaciation would likely have been geologically sudden, ice sheets collapsing and the world flipping from a frozen extreme to a superheated one in perhaps centuries or a few thousand years, the blink of an eye in Earth's history. It was a complete, elegant, self-contained theory, a way in and a way back out, and yet for years, Kirschvink's paper was barely noticed. Openly, only 2 other geologists initially spoke up in support. The idea needed field evidence, or it would remain a beautiful guess. The person who had turned Kirschvink's idea from a guess into a documented fact was, fittingly, someone who'd spent decades in the field getting his boots muddy. Paul Hoffman, a Harvard geologist who had mapped the ancient rock of northwestern Namibia for years, long before anyone mentioned Snowball Earth to him. Hoffman had puzzled for years over a genuinely odd pattern in Namibia's rock, layer after layer of glacial tillite. Then, with no gradual transition at all, a cap of warm water limestone or dolostone sitting directly on top. It looked less like a normal sequence than an abrupt jump cut in the story of a landscape. That's genuinely strange. Limestone and dolostone usually accumulate slowly, over thousands or millions of years, in warm, shallow, life-filled seas. Finding it draped instantly atop cold glacial rubble, with nothing gradual in between, is like finding a tropical coral reef growing directly out of a glacier's terminal moraine. Hoffman realized this was exactly the fingerprint Kirschvink's mechanism predicted. An abrupt flip from a frozen, weathering-starved world to a carbon dioxide-choked super greenhouse would trigger explosively fast chemical, weathering the instant ice retreated. flooding the ocean with dissolved minerals and precipitating carbonate rock almost immediately on top of the glacial debris. And these cap carbonates weren't a Namibian oddity. They turn out to sit directly atop both the Sturtian and the Marinoan glacial deposits on nearly every continent that preserves rock from this age, sometimes nearly 200 meters thick, a single worldwide signature stamped on the aftermath of both freezes. There was a second clue hidden in the same rock: the ratio of two carbon isotopes, carbon-13 to carbon-12, locked into the carbonate as it formed. Ordinarily, photosynthesizing ocean life prefers the lighter carbon-12, steadily enriching seawater, and the rock that forms from it, in the heavier isotope over time. Right around both glaciations, that ratio swings sharply and abruptly negative, a geochemical signature of ocean life's productivity nearly collapsing for millions of years at a stretch. It's exactly what you'd expect from oceans sealed under ice, starved of sunlight, with photosynthesis all but shut down planet-wide. Hoffman, together with Harvard geochemist Dan Schrag, spent years mapping these sequences meter by meter across Namibia, sampling isotopes bed by bed, building a rock-solid physical record instead of just an argument. Fieldwork, not speculation, would settle this. In 1998, Hoffman, Schrag, and colleagues Galen Halvorson and Alan Kaufman published their case in the journal Science, under a title that finally sounded less like speculation and more like a finding: a Neoproterozoic Snowball Earth. The paper wove every thread together into one coherent story: tropical paleomagnetism showing wear, cap carbonates showing the abrupt climate flip, and carbon isotope excursion showing life's near total collapse. All converging on the same conclusion from three completely independent directions. The response was immediate and enormous. Hoffman went on extensive lecture tours. Snowball Earth leapt from an obscure 7-paragraph footnote to one of the most talked-about hypotheses in modern Earth science, drawing in climate modelers, geochemists, and paleontologists from around the world. Try to picture what this actually implies. An entire planet with almost no exposed liquid water anywhere. Ice possibly kilometers thick, sealing the deep ocean away from sunlight and air alike, a white billiard ball spinning silently through space for millions of years at a stretch. A natural objection follows immediately: how could anything survive that? The leading answers point to hydrothermal vents on the seafloor, still warmed from within regardless of the ice above, and possibly thin patches of ice near the equator letting a little sunlight filter through to shallow water beneath. Another question: why did this tip over specifically in the Neoproterozoic? Part of the answer may be that continents at the time were unusually clustered near the equator, changing weathering patterns just enough alongside a slightly fainter young sun to push the whole system toward its tipping point. And why did it take so agonizingly long to build up enough carbon dioxide to escape? Because both halves of the cycle, weathering shutting off and volcanoes slowly refilling the air, are geologically slow processes unfolding over millions of years rather than centuries. Nothing about this story happens quickly, except the very end. That contrast is almost the whole point of the story: millions of years to freeze, millions more to slowly refill the sky with carbon dioxide, and then, by comparison, an almost instantaneous catastrophic thaw once the threshold is finally crossed. Slow trap, sudden release. Taken together, Hoffman and Schrag's work didn't just repeat Kirschvink's idea, it turned it into a testable, quantified, globally consistent stratigraphic pattern, written into rock on every continent that preserves this sliver of deep time. Snowball Earth stopped being a guess and became a documented hypothesis, with real evidence behind it. It's a genuinely satisfying piece of scientific detective work: an odd magnetic reading in the Arctic, a stubborn theorist's mechanism, and two geologists' years of muddy fieldwork in a Namibian desert, all converging on the same extraordinary conclusion about the entire planet's deep past. But not everyone was convinced that the freeze had been quite so total. A serious scientific counter-argument was about to complicate the tidy picture, and it remains very much alive today. The pushback centers on a stubborn biological fact: photosynthetic algae and other ocean life clearly survive straight through both Neoproterozoic glaciations. Their fossils and chemical traces appear before, during, and after. And that's hard to square with an ocean sealed under kilometers of ice, with essentially zero sunlight reaching the water anywhere on the planet. In 2000, climate scientists William Hyde, Thomas Crowley, and Richard Peltier built a coupled climate and ice sheet computer model to actually test the physics, rather than argue about it in the abstract, and published their results in the journal Nature. Their simulations turned up a genuinely different possible outcome. Under plausible Neoproterozoic conditions, some runs produced not a fully frozen ocean, but a persistent belt of thin ice, or even open water, lingering right around the equator, like a narrow tropical seam of liquid on an otherwise frozen world. They called it, informally, the Slushball Earth, a world almost entirely frozen, but not quite. That thin surviving strip of open or thinly iced tropical ocean would have let sunlight through, kept the water cycle limping along and given algae and other life a shrinking but real refuge to hang on inside. The stakes of this debate are real. A hard total snowball makes the ice-albedo runaway feel absolute and nearly unstoppable. A slushball offers a middle path, one where the feedback loop still runs wild, but life gets a narrow escape hatch that a completely frozen planet would never allow. Advocates for the harder, more total freeze push back with the sheer scale of the sedimentary and geochemical evidence. Ice-rafted debris reaching genuinely equatorial latitudes, cap carbonates appearing worldwide with no exceptions, and carbon-isotope swings so extreme they're hard to explain with anything less than a near-total shutdown of ocean life. Later modeling, adding more realistic ocean and sea ice physics, has generally found that an equatorial water belt is harder to sustain stably than the original simulation suggested, nudging some of the debate back toward a harder freeze, though hardly settling it once and for all. It's worth saying plainly, this argument is not settled science. Hard snowball versus slushball has run for over 2 decades and remains genuinely, actively debated among specialists. And that is exactly how science is supposed to look when it's wrestling honestly with a hard, ancient, and incomplete dataset. And here's what matters most, regardless of exactly how hard. The freeze got, virtually everyone agrees on the underlying mechanism. An ice-albedo feedback that runs away past a tipping point, escaped eventually by a volcanic carbon dioxide supergreenhouse. The core physics of the story isn't actually in dispute. It also wasn't necessarily one clean freeze each time. Newer, more detailed work on the older Sturtian glaciation suggests it may have involved repeated cycles of brief thaw and refreeze over its 50-plus million-year span. A messier, more turbulent stretch of extreme climate swings rather than one steady, unbroken deep freeze. Step back and take in the scale of it. 2, possibly more, of these extreme glacial episodes, spanning roughly 80 million years, define the Cryogenian period, literally the age of ice, a stretch of Earth's history utterly unlike anything in the last half-billion years. Keep the timing in mind. This all happened hundreds of millions of years before the first dinosaur, before anything with a backbone, before almost anything you'd recognize as an animal at all. Life at this point was still overwhelmingly microscopic. Bacteria, algae, and simple single-celled organisms clinging on through the worst climate the planet has ever thrown at it. And then, right after the final glaciation, the Marinoan, ending about 675 million years ago, something genuinely remarkable starts showing up in the fossil record, and the timing is hard to ignore. The Ediacaran period begins, named for fossils found in the Ediacar Hills of South Australia. And with it come the first widely accepted complex multicellular organisms, strange frond-like and quilted creatures, among the earliest true animals yet found in the fossil record. It's tempting to draw a straight causal line, extreme climate chaos, followed by a nutrient-rich meltwater flood and a newly oxygenated ocean, somehow kick-starting the leap to complex multicellular life. Some researchers find that connection compelling. Others urge caution, since correlation in deep time is a notoriously slippery thing to prove. To be fair to that caution, plenty of major evolutionary transitions in Earth's history happened without any Snowball Earth event nearby to blame. The most honest statement is that the timing is suggestive and actively studied, not that scientists have proven the freeze directly caused the leap to animal life. Whatever the causal story turns out to be, the sequence continues. The Ediacaran gives way, around 541 million years ago, to the Cambrian explosion. A sudden, spectacular burst in the fossil record where nearly all the major animal body plans alive today first appear. Which means this ancient, almost unimaginable planetary catastrophe may be quietly woven into the deep origin story of complex animal life, including, eventually, us. The frozen world and the first true animals sit right next to each other on the timeline of deep history. Step back and admire the whole detective story. It began as a single, strange, magnetic reading from an Arctic rock in the 1960s. It took a stubborn theorist's physical mechanism, decades of muddy fieldwork across a Namibian desert, and competing computer simulations built by rival research groups to even partially resolve. Each piece needed all the others to matter. Paleomagnetism showed where the ice had been. Kirschvink's physics showed how a planet could actually freeze that far. Hoffman and Schrag's fieldwork showed the aftermath written in the rock, and the climate modelers tested exactly how extreme the freeze really got. Snowball Earth has since become something bigger than one ancient mystery, a foundational case study in how planetary climates can carry runaway feedbacks and hard tipping points, tucked inside otherwise ordinary-looking physics. Reflectivity, greenhouse gases, slow geochemical cycles that quietly build toward a threshold. It even shows up now in the search for life on other worlds. Understanding how a planet's climate can flip catastrophically between two very different stable states matters directly for judging which distant exoplanets might stay comfortably habitable and which might be one tipping point away from becoming a frozen or blistering ruin. So, a paradox first spotted in Arctic rock, and argued over for 6 decades since, turned out to reach far beyond one ancient ice age. Touching how we understand climate itself, anywhere in the universe it might occur. Let's gather what this story leaves us with. First, Earth's climate is not one single, cozy, self-correcting thermostat. It appears to have at least 2 dramatically different stable states, something like today's mild world and a fully frozen one, separated by a genuine tipping point most of us never have to think about. Second, reflectivity alone is an almost absurdly powerful lever. The simple difference between white ice and dark ocean, once it crosses a threshold, can overwhelm nearly every other factor in the entire climate system. No exotic new physics required, just sunlight bouncing off the wrong color for long enough. Third, the very thing that traps a frozen planet can also be what eventually saves it. Sealing the ocean under ice also seals off the process that normally regulates carbon dioxide, and that failure, left running unchecked for millions of years, quietly builds the exact greenhouse pressure needed to break the ice apart again. Fourth, this is a genuinely wonderful model of how science actually works. A stray magnetic anomaly. A 7-paragraph unrefereed footnote almost nobody read. Years of unglamorous, muddy fieldwork. Rival computer models. Decades of argument. And out of all of that, slowly, a real, well-tested, still-evolving understanding of an ancient planetary catastrophe. Fifth, genuine, ongoing uncertainty is not a failure of science. It's a sign of a hard problem being taken seriously. The hard snowball versus slushball debate has run for over 2 decades without a clean final answer, and that's exactly how science should look when it's grappling honestly with deep, ancient, incomplete evidence. There's something quietly humbling in all of this. The ground beneath any tropical beach on Earth today may, hundreds of millions of years ago, have sat buried under a kilometers-thick sheet of ice, utterly unrecognizable from the warm, living shoreline standing there now. The rocks remember, even when nobody is watching. A boulder dropped by melting ice 700 million years ago, or a single magnetized grain quietly locking in Earth's field at that instant, sits patiently in the ground, a silent witness waiting for someone curious enough to finally read it. There's a strange modern echo worth noting carefully. Today's climate is being forced rapidly in the opposite direction, toward warming, not runaway freezing. But the same feedback logic is playing out in miniature at the poles right now. Melting ice exposes darker ocean and land, which absorbs more heat, which melts still more ice. To be careful and precise, today's warming and the ancient Neoproterozoic freeze differ enormously in cause, scale, and speed. But both are proof that Earth's climate system is genuinely capable of feedback loops and tipping points. It does not simply drift along a smooth, predictable straight line. The deepest lesson of Snowball Earth may be this: look for thresholds, not just averages. A small, gradual push applied near exactly the right tipping point can produce a wildly disproportionate, runaway consequence. A lesson worth carrying well beyond the study of ancient rock. Zoom back too, on the sheer resilience of life. Whether the freeze was hard or slush, some microbial and algal life endured the single worst climate catastrophe in the planet's entire history, and not long after, helped kick off a burst toward genuine complexity. That resilience is itself an oddly hopeful data point. It says something remarkable about how tenacious life can be, and how creatively it explores every newly opened niche the instant conditions finally shift, even after the most brutal climate event the planet has ever endured. Return for a moment to the very human side of this story, Brian Harland's decades-early warning that almost nobody took seriously, Kirschvink's audacious 7-paragraph paper that sat nearly unread, Hoffman and Schrag's years of exhausting, unglamorous fieldwork across a remote Namibian desert to finally prove it. It's a reminder that some of science's biggest ideas begin as marginal notes, filed away and barely read, and that they only earn real standing once someone puts in the years of rigorous, patient, often unglamorous field evidence needed to actually back them up. Credit belongs too to the critics. Hyde, Crowley, Peltier, and everyone since who has pushed hard against the hard snowball picture. Science genuinely benefits when capable people try their hardest to prove a popular, exciting idea wrong, and the theory only gets stronger for having survived the attempt. Pull all the way back, and the final picture is almost too strange to fully absorb. An entire planet, twice, may have frozen from pole to pole and equator to equator, sat that way for millions of years, and then thawed in a paroxysm of volcanic heat, with something like us eventually evolving in its aftermath. Sit with the strangeness of that for a second. The tropics, the warmest, most life-rich, most vibrant band on Earth today, were once, twice, the last stronghold, or perhaps the very center, of an ice age so total it's genuinely hard to picture standing on a modern beach. Think back to that beach walker from the very beginning of the story. The next time you see a scratched, wave-smoothed boulder or a strangely striated slab of bedrock anywhere in the world, you may be looking at a genuine message from deep time, patiently waiting for someone curious enough to read its buried magnetism. Trace the whole arc of it, a paradox, glaciers at the equator, a mechanism, an unstoppable ice-albedo feedback, a case built from rock, capped carbonates, and carbon isotopes. An honest, ongoing argument, hard snowball versus slushball. And, just maybe, a hidden hand in the deep origin story of animal life. It's a genuine privilege that patient, careful people, paleomagnetists reading ancient compass needles, geochemists parsing isotope ratios, climate modelers running rival simulations, can reconstruct an event this vast, this ancient, and this genuinely strange, starting from nothing more than ordinary-looking grains of rock. Stay curious about what other obvious impossibilities might be quietly hiding a real mechanism in plain sight. Because glaciers at the equator once sounded exactly as impossible as this idea did, until somebody stubborn enough finally looked closely. If this story stuck with you, do two quick things. Hit subscribe. Neat Science brings another forgotten story back to life, and there's a whole playlist of them waiting for you right now. And tell me in the comments, which part of this surprised you the most? I read every single one. So keep exploring. Your next story is just one click away. I'll see you there.